Hi everyone, today we're going to be talking about some strategies for optimizing the phonetic transcription of archival corpora. So if we really want to understand the diversity of sound systems in the spoken languages of the world, we need detailed analyses of not just the phonological patterns, so what sounds are in the inventories of these languages, but also their phonetic patterns, so how different sounds are produced, what makes them different from one another. And of the 7,000 or so languages in the world, there are very few that can be considered to have comprehensive phonetic documentation, so detailed analyses of the vowels and the consonants and the prosodic patterns and other aspects of the system. And in recent decades, Indo-European languages have very firmly remained the focus of descriptive phonetics, and the Pacific is particularly underrepresented in phonetic descriptions, as you can see from the map on the right there showing phonetic descriptions from the Journal of the International Phonetic Association. So a lot of phonetic description is based on what gets called lab speech, which allows for detailed examination of particular contrasts and speech processes through the elicitation of targeted and controlled and balanced speech data. But in recent phonetic research, there's increasing use of large data sets of natural speech or naturalistic speech as part of a trend towards corpus phonetics. And this has been facilitated by the development of tools and methods that allow us to speed up data processing and analysis. So phonetic analysis of vowels and of consonants and prosody requires quite granular segment level as well as higher level annotations. And these can be extremely time consuming to undertake manually. So achieving automated alignment of phone labels to the speech signals saves an enormous amount of time and significantly increases the possibilities for analyses that can be undertaken. But things like automatic speech recognition and forced alignment methods have largely focused on varieties of English, partly because of the limited availability of suitable technologies, linguistic analyses, and also annotated corpora for lots of under-resourced languages. But there are, of course, archives such as PARADISEC, which house rich language documentation collections. And these really offer us an opportunity to extend knowledge of cross-linguistic patterns, as well as have closer examination of language internal patterns of variation and change. And field recordings housed in archives are typically accompanied by detailed utterance-level orthographic transcriptions, especially more contemporary collections. And these can provide the basis for accurate speech models, which can then be used to rapidly label and phonetically analyze language data. And on the right there, you can see a map showing PARADISEC's holdings in the Pacific region or part of. And so in this study, we're focusing on Nafsan, which is an oceanic language of Vanuatu spoken on the island of Efate in 3 villages. And that's in central Vanuatu. And Nafsan has been the subject of detailed documentation by Nick Teigberg and linguistic description, and also more recent experimental phonetic research. And the data for Nafsan that's housed in PARADISEC includes about 130 narratives, which have been recorded with close to 50 Nafsan speakers during fieldwork undertaken by Nick in the 90s to 2000s. And these recordings are accompanied by orthographic transcriptions in Ilan, as you can see below. And so following processing and preparation of Nafsan data, which sort of this process for anyone who's done this kind of work can be quite involved and idiosyncratic depending on the collection and the materials there. Following this processing and preparation, recordings can be used for speech modeling and to develop and test forced alignment methods. And our aim here is to create a framework that can be used for cross-linguistic comparison of the phonetics of Pacific languages with a focus on central Vanuatu. And so this will be facilitated through the use of a phonetic approach. And what we're reporting on today is work that's still in progress. So we're currently using data for just over 2 hours of speech collected from recordings with 11 women, 11 Nafsan speakers.
You're asking is why use phonetics in this kind of corpus-based automatic speech recognition? And the most important thing from our point of view is that the existing workflows are based on this kind of segment level rather than a higher order level like the word or the utterance. So really getting down to the granular phonetic segmentation. Importantly, even models that do focus on this segmental level or segmental tier, they train mainly on a phonological representation. And largely, we are also using kind of phonological models, but we're trying to bring in as much kind of existing phonetic knowledge about the languages that we're looking at. And this kind of makes the resulting model much more robust. So when you've got a phonological model, often it makes it quite difficult to compare between languages, particularly languages that are not related or closely related phonetically. And a solution is to use one larger phonetic inventory that's shared for all speakers and languages in the sample, with different grapheme to phoneme rules that are language specific. Importantly, to get this kind of model, it requires very careful initial transcription. So it's important to have language data that has been closely checked by native speakers and has had lots of linguistic input rather than just kind of coming straight out of orthographic representations, I suppose. And another important element is having a phonetically transparent orthography. And luckily, many of the languages of Vanuatu have such a transparent orthography. Another key question is how much data is needed for training a successful acoustic model. How many hours of audio are needed, and what other data may be important to be input. So that was probably one of the most important kind of outcomes initially, was to just know how much data to put in. And so we started with this 2-hour set, and we built up from just a single speaker, built up to the 11 speakers that we have currently. And we built tokenized dictionaries, so dictionaries with both an orthographic representation and a phonemic representation, as phonetically accurate as possible. And this all came from the field recordings out of Elan. This was input into the Montreal Forster-Liner, and at this point we were using all data for the training session rather than having one set for training and one set for testing. And testing was performed separately on an unseen set of 15 minutes of audio that just came from a single speaker. And then this meant that we were able to amalgamate the output text grids from the Montreal Forster-Liner, and this could be input into sets of Pratt scripts for databases, or it turned into EMU databases, or also re-imported back to Elan to line up with the original orthographic or kind of linguistic syntactic analyses. Here's a very quick overview of the sort of workflow we were using, with inputs from field recordings, going through to exporting from Elan and cleaning the text grids so they could be turned into phonetic dictionaries, input into MFA, and then at the other side we get text grids. And the important part is the, I guess, the acoustic model that's generated, which we could then use for further analysis, further forced alignment of new data. So the input was approximately these 2 hours of speech, and that's all speech with most of the longer pauses removed. And the training part took approximately 30 minutes on an 8-core CPU, which was a cloud instance, and testing on 15 to 30 minutes of audio was approximately, took about 8 seconds using these acoustic models. So once the acoustic model has been trained, it's very, very quick to do forced alignment on new data. And just to give you a bit of an idea of the output, the alignment is really good, even with just a couple of hours of enough sound speech. So I'll just draw your attention, for those who aren't familiar with the spectrogram here. We have an S here in this first word with a lot of high frequency information. So the frequency there is on the y-axis, the further towards the top is more high frequency excitation in a sound like S. And here we've got a nasal sound with its characteristic antiformants. And you can see that it kind of changes between consonantal information and vowel information, and does a reasonable job at splitting those things up. Now, of course, that's just a first pass, but when, and we should take this as quite preliminary findings, but when we take out the vowel sounds based on midpoints of the vowel, we can see that it does make a very recognizable vowel space that's for all the speakers. So this is, again, based on this 2 hours and 13 minutes, 11 speakers all amalgamated, and there's very clear patterns of the 5 vowel qualities. So you've got the front vowels and the back vowels and these central vowels, but there's also a length differentiation in Nafsan as well, which can be seen here. So you've got the longer vowels, more peripheral in the vowel space. And it's broadly similar to previous patterns that Rosey's found in Nafsan using much more controlled data for CVC monosyllables, and these were all hand corrected, 7 speakers. And here's an example of the vowel space that is this more controlled data. And just so you can compare them directly, we have just made a polygon around them, and you can see that they do have this similar shape. And a lot of the, I guess, outliers that are outside of this polygon probably are showing, first of all, that there's different speech rates, different modes of elicitation for the corpus data, and also many different speakers. So there's likely to be more diffusion for some speakers and more kind of tightly controlled vowel spaces. In terms of duration, it's very easy to kind of show some duration information, and here we have long vowels and short vowels shown, and you can see that the long vowels are on average much longer in duration, but there is overlap that needs to be looked at. And another important aspect that is shown in this diagram is that the output of MFA, the Montreal Forced-Liner, is in fact has durations binned into 10 millisecond lots. And this can make fine measurement difficult, and also make statistical analysis a little bit more challenging.
So from here, what we want to do is complete the preparation of the remaining corpus data, which is quite a lot still to get through, finalize the modeling and the alignment workflow, and then integrate data at utterance and other levels. And you can see an example of what that might look like below. So not just that orthographic transcription, but then if there's other annotations that go with this sort of data that have interlinear glossing, for example, those can be reintegrated with the MFA output, and then create an EMU database that can be used to have a standing phonetic corpus that can be used to interrogate different aspects of the phonetics of Nafsan based on all this rich natural speech. And then from there, what we'd like to do is test the framework with data for other languages in the Awhata region of Vanuatu, many of which are represented in PARADISEC as well. And so what we can see so far, even just in these early stages of the work, is that materials in a typical language documentation corpus can be used to train very effective speech recognition models, especially if they're adequately prepared. And this can lead to new phonetic insights for under-resourced languages. So we end up being able to go from having, a bit over 1,000 tokens that give us a nice example of the contrast in the language, to having nearly 18,000 vowel tokens just in this 2 hours of data that we can work with across a number of speakers, that we'll really be able to tease apart and interrogate to see what patterns of variation there are across speakers, patterns of language change potentially, and just having that scale really makes so much more possible. And the approach that's been used here really draws on the extensive information about Nafsan from the linguistic analyses and the many contributions of community members. So it's not something that can just be rolled out across other language data without knowing anything about those languages. But the approach here really does expand the possibilities for phonetic transcription because it offers us a really excellent starting point to start using data for other languages which are geographically and genetically close to Nafsan and can be expected to share certain aspects of the sound system. So even if we don't have all that much data available for those languages, we'll be able to start to build on what we've got for Nafsan and extend it to apply to those languages, and then hopefully begin some robust cross-linguistic comparisons for Central Vanuatu. And so here's some references that you can look at in your own time. And we'd just like to finish by firstly thanking all of you for listening, and importantly, thanking all of the Nafsan speakers who've contributed to this work over many decades, and also to our collaborators, Nick and Janet. Thanks.